Okay, I guess we can start. So today you will have your fourth practicum on knowledge distillation. So I don't remember if you have this in your lecture already. I guess you did. But knowledge distillation is when you have a bigger model, like already trained, and then you try to use the information from the bigger model, like for example, the output distribution or the hidden state, in order to train a smaller lightweight model with the goal of having faster inference time. So that's what we're going to do in this notebook. I hope that everyone have time to have a look at this notebook, but even if you don't, I guess it's okay. You can still kind of follow my explanation. Um, yes, so in this notebook, we will look into how to modify model classes to extract hidden representation and use them for further calculation. So instead of just returning the hidden layer and do normal training, we would also need it to pass it along to train a smaller model. How to modify regular training loops in PyTorch to include additional losses, as in the distillation loss, in addition to the normal cross entropy, and how to improve the performance of lightweight model using more complex model as teacher. So this is the prerequisite, but I guess the free GPUs on Colab should be enough. Yes, so first we just, as usual, have the code to load all the torch packages. So the task this time is again also image classification, and the data set that we're going to use is Cipher 10. So they have 10 classes. And again, the objective is to predict one class per image. And here's some information about the image. So they are RGB, 32 by 32 pixel, ranging from 0 to 155 values per cell. So similar as last time, we also have the code to do normalization on the image, as in we would subtracting the mean and dividing by the standard deviation. So this code is already provided for you. Usually when we implement stuff, it would be good if you make your code as quickly reproducible. No, maybe it's better to say as quickly executable as possible. So here's the block of code where you just simply select a very small amount of images in order to have a very quick round of test training and testing just for implementation purpose. But otherwise, we would take the whole data set. Yes. So the next thing we do is to define model classes and utility functions. Um, so we would define two different architecture. So both of them are convolutional neural network, but one of them is going to be a bigger, fancier model to learn all the complicated features. And then one is also CNN, but smaller as a student model. And we would keep the number of, we would have different number of layers, but then keep the same number of filters. Yes, and after all the CNN layers, we would have the final classifiers part of the model, which will output the probability belong to each of the 10 classes. So here's the code. Yeah, so I guess this part is quite straightforward. You just define the model with convolutional layers and then ReLU and MaxPool in the middle. The classifier part is going to be some linear layers, and it's important that in the last layer you project to the number of classes. Otherwise, I guess this is quite flexible, and if you have time and if you want to play around, you can also just change it. The forward pass, also quite straightforward. And the lightweight neural network model, we kind of do the same, but just have smaller number of layers and also smaller number of, smaller hidden dimension. So here's 1024, and for the bigger model is twice the size. So this code is already pre-given. So next, we will define two functions, one for training and one for testing the models. So for this part, this is the standard way for you to train normal neural network model. So there's no installation part, yes. So if you have the target vector and then you have the output layer, just calculate the loss between them and backpropagate. Do the same for the student model. So at this point in time, it's still completely independent. And so below is the function for those two. So the training function would do the training loop, and then the test function would output the accuracy on the test set. So the next part is the cross entropy run, in which we just simply run the predefined function on our two separate model and check their accuracy. So as you can see here, first we initialize the big model and then we initialize the smaller model. So the test accuracy achieved on the big model is going to be 75.78% for for this model. And then for the smaller model, we do. Oh yeah, there's one crucial step if we want things to be comparable. So here we are training the smaller model from scratch, just so that we have a comparison to the distilled model later. So in order to have a fair comparison, it would be good if the two models have exactly the same initialization. So that's what we're doing here. We set the seed, initialize both model, and then in order to double check whether our initialization between the two models are exactly the same, we just print the norm of the first layer and see if we achieve the same value. So that's what we have here. And then we also have some code to report how the size of each model. And we can see that the teacher model is much larger. And then we have the code to train our student model. And then we arrive at the test accuracy at around 70%. So it's like around 5% lower than the teacher model. Here's just summarization. And now comes to the interesting part. So the first type of knowledge distillation is that you try to make the student model to output similar distribution as the teacher model. So given one data point, instead of trying to make the student model to output one for the correct class, now you would try to make the student model to output exactly the same output distribution as the teacher model. So for example, if the teacher model have like 0.9 for the correct one and then 0.1 for the others, then that's what we want to mimic. And I guess the motivation here is that for the model to be more robust towards different noise in the input. Yes. So one of the problem is that most of the time neural network model are kind of overconfident and it would already assign quite a high score onto the correct class that is predict. So technically, if you don't do anything about it, then training with knowledge distillation with a teacher model would technically be the same as training with a normal training one hot encoded data, because then the distribution is still very picky, like only one values get most of the probability mass. So what people do is that they add a scaling temperature, T, like in this formula, and then thanks to the scaling temperature, we kind of distribute the probability mass of the correct of the output class into the other class. And then, so it's a way to make our distribution a bit more uniform. Yes. And in addition to that, we would also define two hyperparameters to balance between the two losses. So one is the weight for our distillation loss, and one is the weight for our normal cross entropy loss. So just by tuning these parameters, we will tell the model which task is more important. So technically, this is the illustration of what I just described. So for the output layer, this is after softmax. So this is just the two probability distribution, one from the teacher and one from the student. And for the student, except for the normal loss, we would also take into account the distillation loss here. Yes. And yes, and the loss that we use to force these two distribution to be similar to each other is the KL divergent, and it is predefined by the formula. And I think in PyTorch it's already pre-implemented as well, so you can just take out of the box. Yes, so this is your first implementation task to implement the training loop for the knowledge distillation. So the first step is to forward with the teacher model. And because we don't want to change the weight of the teacher models, because our main goal is just to get the output distribution out to teach the student model. So we would not do anything with the teacher model. So that's why we do here torch.nograd. And then the next step is to forward with the student model and also get out the student logic. And we would want the loss to kind of pull these two closer to each other. No, sorry, we should pull the two probability distribution closer to each other. So it's like after the softmax layer. Yes. And then we have the formula for the distillation loss that we defined above. And then we have the normal cross entropy loss given the labels and the logic. So like in normal training process. And then we sum the two loss together, taking into account the weight. And then that's it. And afterward, we just do backpropagation and optimization just the same as before. Yeah, so that's the code for distillation. And then here's the performance. So as you can see here, this is the recall of two result before, but here the student accuracy with cross entropy loss with this kind of distillation using the output distribution doesn't seem to be working in this case. I'm not sure why. Maybe it's also because the hyperparameter is not well tuned yet. But one explanation could also be that if the student model can have more information on a more deeper layer inside of the teacher model, maybe it would help more than just taking the output distribution. So that's why we go to the next type of knowledge distillation. But so far, is there any question on this first type? Okay, so then the next type of knowledge distillation here. So instead of minimizing the difference in the final probability distribution, we try to minimize the difference in the hidden state, as in the last state before the values are fed into the classifier. So for this, we would use the cosine embedding loss, which I think is also implemented by PyTorch already. However, there's one problem. As I mentioned before, the teacher hidden state is twice as large as the student hidden state. So it's not as straightforward for us to just feed those two hidden state into the loss function because they have mismatch in size. So we have to include another pooling layer. So as you can see here, yeah, so the first, so to implement this forward function for the student model, we first need to, I know this is the modification to the teacher model. Yes, so we first to flatten the output, and then we need to do a pooling layer with size 2 in order to shrink the size of the hidden state by 2, and then we will have matching side with the student. And in the return function, instead of just returning the state, we would also returning this hidden representation to be used later for the student. And then for the student, we do the same, also flatten, so that we get them ready to calculate this additional loss. Yes. And then we also have this initialization of a base model for calculation, similar as before. And here's some code for you to verify whether you already have the same shape between the teacher and the student model for the loss. And as you can see here, both of them now output 1024. Yes, and then we have this diagram which kind of describe what we discussed before. So this is the teacher hidden state, and it's much bigger than the student hidden state. So we have a pooling layer, having them into the same size, and then calculate the cosine loss here. And then we would do that, we'll do this loss in combination with the normal loss for the student model. And then your next task is to complete this training function for the model. So again, we do torch.nograd for the teacher because we don't plan to teach the teacher anything. But the difference here is now we need to save the hidden state. And then same to forward pass for the student model, but remember to save the hidden state. And then we use those two hidden state between the teacher and the student to calculate the hidden representation loss. And then the label loss, the same way as before, the normal standard loss as before, and then combine the two loss together the same way as before. So that's all the modification. The test function also need to be modified, but only because we're now returning two values instead of one for the function. So this is just technical implementation details. I guess there's nothing changed, particularly like theoretical wise for the inference pass. And then we can see the result. So the test accuracy now is 70%. So it's better than when we use knowledge distillation on the final output probability, but still is not significantly better than the base model yet. Is there any question for this part? Okay, if not, then we can go to our last type of knowledge distillation. So the way we do things in the above section is that we try to force the student model to output, to have the exact same hidden state as the teacher model. So this is a bit problematic because we can imagine that when we train the student model, maybe it learns different types of knowledge. So maybe it doesn't make too much sense to force those two to be exactly the same. So it would be better to have some sort of map between those two representation instead of forcing them to be exactly the same. So for this example, we would add another regressor part to the model in which we just transform one hidden state to the other. And then maybe our loss will make more sense. So here we're just printing out the shape of the hidden state. So they technically are the same, but just different in the number of filters. So this is the diagram that illustrates how this will look like. So yeah, instead of like before trying to calculate the loss directly between these two with only one pooling layer, because pooling layer, there's no trainable parameters. So pooling is technically, there's no knowledge mapping. So here instead we will have a regressor that just transform the student hidden state into the teacher's hidden state. And your next task is to implement that. So here's the first to do where you just simply save the feature into variables and return it along with the forward function. And then for the student model, you would include a regressor, which is a convolution layer that maps the hidden state of the student to the teacher. And then in the forward function, you would make use of that regressor and then return the mapping so that we can calculate the loss later. Next, we will modify the training loss again. So same as before, we do forward pass with the teacher with no grad and saving the feature map. for the student, do the same and saving the reverse feature as well. And then we calculate the mean square error loss between those two. And here it will work because the shape of the two representation is the same. And then here again, label loss of the normal standard task and summing the two loss together, taking into account the weights. And next we evaluate the model, and you can see now the test accuracy is 71.2%. So now we finally have an improvement. Yes, I guess that's technically all the implementation. So again, the idea for knowledge distillation here is that we try to have a smaller model that try to match the performance of the bigger model as much as possible. And the saving, I guess the training would be either the same or more because now we have an additional loss. But the goal here is not to save the training time. The goal here is that we want to have a smaller model that run faster during inference time and with lower latency. So that's what we kind of try to achieve. And here, because we didn't do a very fine-grained fine-tuning of all the hyperparameters, we improve the performance of the student model over the student model that is trained from scratch, but still we haven't been able to reach the teacher accuracy yet. But I guess that's one way to have better performance, but also lightweight implementation. So yeah, I guess that's it. Does anyone have some final question? Or if you come up with anything when you're home, you're also free to just ask me on Elias or send me an email. So thank you for attending.